Hello to everyone, I'm Marco Maurizi and I'm a PhD student at the Department of Mechanical Engineering at NTNU. Today I'm going to present a brief review on 3D effects on friction mechanics, based on the paper presented for the virtual conference on structural integrity. Why do we need an overview on that? First of all, notches and cracks are present at every length scale. Here an example is the Olympic Stadium in Athens, Greece, or Margaret Hunt Hill Bridge in US, where a lot of wells and notches are present. But also at smaller scales, here an example is beam-based architectural material where notches are inherent at the intersection between beams, and therefore from nano to micro scale notches play a fundamental role in brittle failure and fatigue crack growth, but it's being recognized how 3D effects can play a vital role in this assessment, and while standards do not take into account these effects. Linear elastic friction mechanics is the analytical framework where we're going to present our review. So these are the famous scientists and fathers of friction mechanics, but their theories were based basically on 2D plane elasticity, so on the plane stress condition or on the plane strain condition. There are some phenomena not well explained by 2D theory. For example, here the mixed mode friction criterion is reported, and it's shown how experimental results do not fit very well with the theoretical prediction in plane strain condition. And another example is that of a strength scale effect, where the linear elastic friction mechanics prediction does not fit at all with experimental results. Moreover, another example is that of both fatigue crack fronts, where at the corner points, therefore at the intersection between the crack front and lateral surfaces, a different stress singularity occurs, and this is called 3D coordinate singularity. I will show you later what it is. However, standards are still based on 2D plane elasticity, and this could represent a problem for the failure assessment of materials. Before to introduce the main numerical results and theoretical ones on 3D effects and friction mechanics, what is necessary to understand is the basic idea behind the 3D analytical frameworks developed in the last 5 decades. The main assumption is in fact the Kahneman-Magnitz hypothesis of generalized plane strain, where the third component of displacement field is considered to be dependent on Z, leading to have a strain component epsilon ZZ to be constant along the thickness. Under this hypothesis, Lazzarini and Zappalorto proposed a new theoretical frame, which is based on two equations, an harmonic equation and a biharmonic equation, where phi is the classical in-plane every stress function. Moreover, the 3D eigenvalue equations are recovered, and the skew-symmetric part of the loading is the only part that generates an out-of-plane shear stress singularity. The main implications from this theoretical framework is the dependence on Z of the shear stresses. Therefore, the mode 3 stress intensity factor, the notch stress intensity factor, depends and is the only which depends on Z, therefore it varies along the thickness. Additionally, the eigenvalue solutions by the analytical equations fit very well with the numerical results, even if these are being averaged on half of the thickness. And this could represent a problem because their singularities, as I've said before, vary along the thickness. So the 3D stress state region around cracks or V notches can be represented like this. In fact, in green we have a process region, in yellow the 3D influence region, and the dashed blue line is a K-dominant zone. So, and outside of this we have the region of plane stress condition. It's been observed how the 3D region is encapsulated by the K-dominant zone and controls the process zone, therefore the fracture. And at the end, the region of plane stress is recovered outside of the 3D stress state region after a radial distance of about the plate thickness. Therefore, local and far-field modes are considered, where these latter are simply the modes of the fracture parameters recovered by the plane stress conditions. Recent finite element results have shown how the mode 1, mode 2, and mode 3 stress intensity factors change along the thickness and with the Poisson's ratio here indicated with 1, 2, and 3. So therefore, other results on that is that the in-plane local and far-field stress intensity factors are related to each other through a linear relationship and by two functions f1, f2, dependent on the z-coordinate along the thickness and the Poisson's ratio. But the main two defects are basically the shear coupled modes and the vertical singularities. We have the mode 0 induced by in-plane loading, which is the something like mode 3 induced by a shear in-plane mode, and it's been observed how the primary mode stress intensity factor, in this case the K2, is equal to the far field applied stress intensity factor at the midplane and increases as the free surface is approached, while the stress intensity factor due to the mode 0, in this case the local induced mode, varies from 0 at the midplane to the maximum before the free surface when it drops down suddenly at the free surfaces, and its nature is explained by the Poisson's ratio, because with the Poisson's ratio equal to 0 we can observe a stress intensity factor in mode 0 equal to 0. So other works confirm these numerical results for cracks and V-notches, as here is shown. But both for cracks and V-notches, the existence of the induced mode, even when the primary stress intensity factor K2 is equal to 0, has been proven. In fact, for V-notch, for example, when the stress singularity, in this case the eigenvalue, at certain V-notch opening angle reaches the value of 1, by finite element modeling has been observed how the shear stress components of tau xy due to the primary mode 2 remain constant because the singularity disappears, while the tau yz shear components remain with a singularity. By increasing the V-notch opening angle, in this case, for example, reaching a value of 120 degrees, the stress singularity of mode 2, the primary mode, disappears, while the tau yz component remains singular. Therefore, the singular mode 0 can govern the failure conditions even when the primary shear mode is not singular, and this is fundamental for the failure assessment. The dual couple mode to the mode 0 is the mode 2 induced by antiplane loading. Here the audience can see a scheme of finite element model loaded by shear out-of-plane stress, and where local deformation similar to the mode 2 are presented. If we look at the stress intensity factors, we can see a different behavior with respect to the mode 0. In fact, the mode 3 primary mode stress intensity factor K3 goes from a unitary value on the midplane to 0 values, while the mode 2 K2 stress intensity factor goes from 0 on the midplane to a maximum on the free surface. The Poisson's ratio dependence of the couple mode 2 stress intensity factor is not reported, and this could explain the nature of the couple modes. In fact, the mode 0 induced by in-plane loading is thought of as generated by the Poisson's ratio, while the mode 2 induced by anti-plane loading is thought of as generated by a mechanism of redistribution of the transversal shear stresses at free surfaces. A lot of works have confirmed these behaviors for the stress intensity factors and for the stress components, and therefore the coupled mode could shift the failure location from the midplane to the free surfaces, and this could be assessed by using, for example, the air strain energy density that in the case of Book et al. Has been used and confirmed that failure location shifts from the midplane to the free surface. Additionally, the singular in-plane coupled shear mode can also arise from a K3 equal to 0 as the previous coupled shear mode, and therefore a singular coupled mode 2 can control failure even when the primary mode is negligible. With regard to the 3D stress state zone, which is completely encapsulated by the K-dominant zone, and under dimensional considerations, the deterministic scale thickness effect on coupled modes has been observed. In fact, here we can see how, looking at the sign of the exponents, for mode 0, thicker plates leads to a greater influence of the K0, while for the coupled mode 2, thinner plates lead to have a greater influence on K2, as here the difference between the strength of the singularities is highlighted. The other important defect is that of corner point singularities. In fact, it's been noticed that at the intersection of the quark front with the free surfaces, another singularity occurs. For the sake of brevity and for the limited time, we don't have time to show the main theoretical results of Bajant, Estensoro, Bentham, and Puck. However, we would like to highlight the famous contradiction on the mode 3 stress intensity factor near corner points. In fact, Bajant and Estensoro predicted that the stress intensity factor in mode 3 should tend to infinite, while the linear elasticity says that the K3 should converge to 0 to respect the boundary conditions of free surfaces. In fact, numerical models have proved this, are in agreement with the linear elasticity, and the K3 drops down near free surfaces. However, recent finite element results on cracked plates and disks have proven how the stress component tau yz is not a straight line on a log-log plot, leading to a stress intensity factor which varies from values of about 0, far away from the crack tip, to higher values, so to finite values near the crack tip. Therefore, non-realistic values of K3 could be computed in these works, and additionally, non-realistic values of the strength singularity for the tau xy, therefore the mode 2, could be computed because they have been found to be function of the thickness. But the authors think that at the corner points, we should consider sum of two singularities in light of the numerical results and theoretical considerations as the sum of stress intensity factor and the stress intensity measure due to the vertex singularities. Thank you for your attention.